Thank you very much for inviting me to participate in this session on such an exciting time in brain research and also in artificial intelligence and neural networks. I'm very pleased to introduce Terry Stanowski, who is Professor of Computational Neurobiology at the Salk Institute for Biological Sciences, where he's the Francis Crick Chair. Terry is a pioneer in the field of computational neuroscience and also an experimentalist, and I actually can't think of an area in neural systems or cross scales that you haven't had some impact on. I was very surprised to learn that you are one of 10 individuals who is elected to all 3 national academies, so engineering, sciences, and the Institute of Medicine, which I think really speaks to your transdisciplinary impact. And more recently, I understand you've been involved in the BRAIN Initiative. You've been an architect on President Obama's BRAIN Initiative and an advisor to the NIH director on this multi-million, if not billion-dollar project to decode the brain. So I'd love to learn a little bit more about that as we go along. I'm also pleased to introduce Richard Socher. Richard is the CTO and co-founder of MetaMind, a startup here in the Silicon Valley, I believe, which just launched in December with $8 million in funding from Mark Benioff and Khosla Ventures. So Richard just also completed his PhD in computer science with Andrew Ning and Chris Manning. At Stanford University, and has taken some of the insights that he has gained in neural networks and artificial intelligence into this new company. And the company's mission is really to take cutting-edge AI advances and bring them to non-experts. And I believe you're involved in everything from social media to medical imaging. So, Richard, I'd love to just start with you. If you could explain a little bit about this neural network, deep learning, that seems to be quite popular and quite exciting. And so what is it in not too technical terms?
Right. So deep learning is a type of artificial intelligence, a set of tools or a set of algorithms that really go beyond traditional machine learning in that there's less human expert knowledge required to make them work. And so to give you an idea, they can do anything from classifying CT scans of the brain to classifying social media messaging. And all you need to give it is the raw input, the text, and an output that you would like to predict. And then they will learn how to represent this input in some successively more abstract representation such that it can then classify it. So to give you an idea of what I mean by this, in computer vision, for instance, it used to be that experts looked when they tried to classify dogs versus cats, or this car make versus that car make. They looked at a bunch of features like, oh, it's these edges, and maybe we want a circle here for the tire. And then once we knew, okay, there should be this kind of circle for the tire and this kind of straight edge for this kind of particular trunk of the car, now we give that to an algorithm, to a machine learning algorithm, to kind of just weight the features automatically. And now what you can do is you just give it a couple of images and it will automatically learn how to represent the image to a computer algorithm to then distinguish very well between any classes. So this kind of technology enabled us as a company to really go and classify satellite images and classify standard car images, or one thing I'm very excited about, medical images. So retinopathy can be classified, CT scans of the brain can be classified as well. And what's fascinating is it's the same kind of algorithm that can classify these medical images that we can also use to classify social media messages and sentiment analysis. So is this a positive tweet about your company or your organization, or negative?
So I feel like I have heard about neural network kinds of technologies since I was a graduate student in the late 80s, and I know, Terry, you did some very seminal work in this area. There was a lot of hype then, it died down, there seems to be a lot of excitement now. Is this real, or is this another part of the hype cycle? And if it's real, why now?
Well, it was apparent to everyone back in the 50s when artificial intelligence just got off the ground that there are 2 different styles. One is programming, where you sit down, an engineer sits down, figures out how to put together a modular program that would be able to identify an object in an image, or be able to move a robot. And the other approach is one that biology takes, which is you learn it. You learn it through experience with the world. And in the 50s, unfortunately, computers were in the kilohertz range, and programming was much more efficient. And so it was possible to make more progress. Learning is very computation intensive, but it's very labor non-intensive. And eventually what's happened is that over the period of 60, 70 years, the two have crossed, where now it's actually cheaper to learn because computation is so cheap and data are so abundant that it's much more efficient to have a learning system solve the problem than hire an engineer, write a program. It's very labor intensive. Now, you mentioned what happened in the 80s. So Jeff Hinton, who's here at Google, and I were the first to come up with a learning algorithm. That's a way of changing the weights on the different layers of the neural network in order to be able to create the representations you need to be able to solve a particular problem. And it was called the Boltzmann machine. That was back in 1983. Unfortunately, computers back in the 80s were like megahertz machines, the VAX series. And it was very limited how large the network could be. A few hundred units. I, for example, had a network called NetTalk that could take English letters from words and pronounce them in English, which was a very, at the time, a linguistic task that was actually very difficult to program. Well, that was a little bit of the 21st century technology in the 20th century because, in fact, we could only do one layer of what we call hidden units. Now it's possible with computers that are in the gigahertz range and with servers that have hundreds of thousands of cores to do networks that are 12 layers deep. And that's about the size of the different cortical layers that we have in our brains. And what we've shown is that it scales. And this is the big secret of AI, is that there are some algorithms that scale very poorly because as the problem gets more difficult, it just takes exponential time. That's NP complete. And there are other problems, and apparently a lot of the problems in vision and motor control and classification are ones that scale very, very well on these architectures. So that's really the breakthrough that's occurred, is the fact that we've reached the point now where there's a threshold amount of computation power to be able to take advantage of the same algorithms that the brain uses. Now there's one other thing that you have to take into account, okay, just to calibrate things here, right? The biggest deep learning networks that I know about, I mean there may be some secret ones that Google has, but at least the ones that I know about have 1 billion weights. Those are the connection strengths. 1 billion parameters. That's a lot of parameters. Well, in 1 cubic millimeter of your cerebral cortex, there's 1 billion synapses, and those are what are weights in the artificial networks. 1 cubic millimeter, right? So the cortex is vastly greater in terms of the amount of computational power that it has. Not only that, but the cortex is only one out of a few hundred processors that you have in the brain. There's another one called the basal ganglia, which is important for reinforcement learning. That's learning through practice. And recently, DeepMind coupled the deep learning hierarchy with reinforcement learning to learn how to play Atari games. And so we're gradually building bits of the brain and incorporating them and making the systems more powerful.
So do you agree with that? Is that sort of the technology that you're using now in MetaMind?
Yeah, so I guess in general we're only very loosely inspired by the brain. We're not, in some ways, computer science is an interesting area in that it's somewhat of a science, but there's also a lot of engineering. And sometimes if you can, it's kind of similar to, do we want to fly like birds or do we want to fly with airplanes that don't flap their wings? And so in some ways, we just need to understand aerodynamics, and then we can try to abstract away from the specifics we see in the natural world and just try to build certain algorithms that work incredibly well. I do agree that the learning versus specifically programming for each task, that is a very fundamental idea that we can now use. But I wouldn't say some of the algorithms that we're building, I'm not a brain expert, so my hunch is that it's unlikely that they're exactly doing what the brain does.
Yeah, I think that was something Steve Jurvetson referred to in the first panel today, this idea that we're now able to evolve software in a way rather than having to know up front. We can parent to this technology as it grows and does things that we may not be able to specify exactly. So can you give me examples of things, you sort of talked about it, things that this technology does particularly well and where it will impact the economy, and then examples of things that we still can't do very well?
It's a good question. So I think the impact on the economy will be quite profound, especially on the job market, in that whenever you have a task that is very repetitive, you keep looking at pictures and then you write down a pathology report, or you keep driving along a road that, and especially in the US, is quite straight for very, very long stretches. Those kinds of jobs will, in the next decade or two, I think, be first made a lot more efficient, so we can, radiologists can look at a scan, sees a report that is automatically generated and checks and make sure it's correct. But eventually, a lot of these things can be automated, and so I think there are a lot of tasks, and several of them we need to, be also careful about the ethics. As soon as there are human lives involved, we need to be very careful about what kinds of things are we comfortable. Do we want to really show that statistically the algorithm makes many fewer mistakes than a human before we let it loose on very important tasks. So I think there will be a lot of tasks that can be automated with deep learning technology. The more education you're required to do your job, I think the harder it will be to automate that job. So I think education is something very crucial, and obviously creativity is something that I don't think we've tackled in any sort of convincing way yet with deep learning. So very creative, artistic kinds of jobs, and those that require to incorporate a lot of different kinds of information will be harder to automate.
Do you have any thoughts on what we can't do well yet?
We don't understand how the brain works. Everybody has one, and I'm sure you've all thought about, why did I make that decision? And things that you do which is absolutely, without thinking, like, reach out for a cup or recognize somebody. Those have turned out, our intuition is completely wrong about them. We thought that those were going to be the easy, trivial problems because they were so easy for us. But they turn out to be the most difficult computational problems, still unsolved, despite the fact that deep learning is making progress. The fact is we're far, far away from human capability in any of those domains, except in very narrow ones that we have a huge amount of data. So what's really at stake here is understanding some principles that will allow us to create appliances, devices that will help us as human beings solve difficult problems that we spend a lot of time doing now, like driving is a good example. But there's so many other expert tasks that we, take a tremendous amount of education and learning, and at the end of the day, if we could automate that, we could free up minds for doing creative tasks that are much, much more satisfying. Now, so I'm the president of the NIPS Foundation, Neural Information Processing Systems Foundation, that was founded 27 years ago by Ed Posner, who was a professor at Caltech. And this is the meeting. It's now the premier meeting in machine learning, and I just learned that, in fact, you've been there ever since you were a graduate student, and it's very nice because it's grown enormously. Last year in Montreal, we had 2,500 attendees, and I can only recognize a small fraction because they were all much, much more younger than I was. But what's exciting is that this community is just tremendous amount of energy. If you could only have been there and seen how much raw intellectual power and the new principles that are coming out of this. There are mathematicians who are actually analyzing these networks and coming up with a deep mathematical understanding of why they're so powerful. We didn't know this. It was empirical up to this point. We now know it's because there are saddle points up there rather than local minima. So this is an exciting time. This is unprecedented in terms of the potential applications, in terms of, and my favorite application is the brain. It turns out that as part of this advisory group to Francis Collins, the director of NIH, we were asked to come up with technologies and get engineers involved in helping neuroscientists. And it turns out one of the biggest applications of machine learning is going to be in analyzing large data sets, recordings from the brain. Right now, we can record from about 100 neurons at the same time. In 10 years, the goal of the Brain Initiative is to be able to record from 1 million neurons at the same time. We're never going to be able to do that with old-fashioned techniques of plotting graphs. We're going to need deep learning to be able to just get off the ground. And not just for recordings, it's also going to be for connectomics, figuring out the wiring diagram of the brain. It's going to be for analyzing behavior. And that's probably going to be one of the big breakthroughs, is that we now can actually analyze animals from flies up to humans, what are they actually doing? Not just, whether they're sitting or walking, but how are they walking? You can tell a lot from a person's health by just looking at what they look like. A physician, a really good diagnostician, can walk into a patient and within 2 minutes, by looking at them and just observing, figure out what their state of health is. And that comes from literally years and years and years of experience with other patients. That's learning, and that's what we're trying to do with these networks.
It sounds like there's a really great interplay between sort of the advances in brain theory and the technologies that you're able to apply and back into understanding the brain. Do you think that advances in brain science are going to inform what you do at MetaMind?
In a very loose way, I think. So one of the things that I'm most excited about, and that we're actually not good at right now, but we're on the brink of getting much, much better at, is natural language understanding. Really being able to give an algorithm a lot of legal documents, a lot of medical documents, and then having it just understand, what's going on, and then being able to get queried and really ask like complex questions that aren't just keyword search, like, oh, I just try to find this paragraph in here. Here's where you may find the answer, which is what Google does right now, for instance, but here is the answer, and just learning that. And so I think there, in neural networks in particular, recently we started working with memory, and that is certainly like a concept where you have certain parts that deal with temporal information, and you have certain parts that in the brain also that deal with memory retrieval and things like that. And so in those kinds of abstract ways, we're definitely inspired.
There's certainly more to ask, but I want to see if anybody in the audience has questions, because I'm conscious of the time. I think there's a hand back there, if there's a mic. Here,
no,
the
you
mic's
need the
coming.
mic.
My name is Dr. George Krusik. I'm a physician, and I was thrilled to see Terence comment about that we don't understand the brain. That's great. I wonder if you can reconcile Vinod Klosa's comment that we as physicians will be replaced shortly by machine learning, and I'm just wondering when I can introduce them to my patients.
So I don't think you have to worry about being replaced, but in fact what I hope will happen is that your time will be freed to actually explore, what the implications are of the symptoms that appear. But in a sense, having an intelligent assistant. And really what's happening is that this will create appliances that are going to amplify your intelligence. And my examples, we already have an example of that. We have chess playing programs that now can play as well and better than the world's best chess players. What's happened is that replaced, have people stop playing chess? No, it turns out that everybody's game has increased because they can play the best players on their computer. And this also means that somebody in a village in Norway can become the world's chess champion, Magnus Carlsen. So this is going to happen in medicine. You're going to have ordinary docs becoming super docs.
And I think one thing that's important to add here is that certainly in the US, people have access to really great doctors in at least most of the cities. But if you go into the developing world, people don't have access to any doctor, and there are actually literally people dying because the surgeons don't have radiologists tell them where to go. And so if the world's best doctors can instill their knowledge in algorithms by training them, giving them lots of examples of, here are the symptoms that I see, here's what I think is happening. If you can instill that knowledge into algorithms, you could help a lot of people right now who don't have any access to good doctors.
Well, thank you very much. I'll now have more time to fill out the electronic medical record after your visit.
Thank you. That'll be great.
Dave?
Hi, I'm sorry to intervene, but, I think Terry's already more or less answered this, but the Kurzweil idea of the singularity, is that something you buy into, in either one of you, and how do you factor that into this discussion?
Where are you?
I'm here, sorry.
Oh, I'm sorry. You know, I think too many people have fallen into the singularity. It turns out to have consumed a lot of people's thought. I think that we're far away. This is just the beginning, and we're many e-fold away. It's just to take the raw. I already told you that we can only simulate in a very crude way, artificially, what's happening in a little tiny little pea of the brain, and in order to get to the point where we can solve the really difficult problems, it might take 10, 20 years. Or 100 years, we don't know. In fact, the reason why we have a brain initiative is to accelerate progress in understanding the brain and to accomplish in the next 10 years what otherwise would have required 100 years. So I think that there is predicting the future is very difficult, and I applaud those that are thinking about it. But the track record of humans predicting the future is really poor, especially the experts. Experts are really good at telling you what's not possible. It's the young people who actually make it happen.
And I think it often distracts from the real issues. So in medical, like having certain ethical requirements for algorithms to make interventions, especially in military applications, making sure that there are ethical standards for when these kinds of computer vision techniques or robotics techniques can be used and should be used. And so I think it distracts a lot in both the positive and the negative way, right? When you can say the singularity, well, now you have an algorithm that will solve cancer and all these other things, and other people are then worried and think, oh, the Terminator will happen and we'll all get killed in Skynet and all that. And I think both of those are quite distracting from actual issues that we have right now. Eventually job issues right now, just sort of ethical issues.
And I should mention that human mental disorders is one of the biggest problems on the planet, especially as our population ages. We all know, we heard it talk about Alzheimer's. Well, half the people in this room, if you live to 80, 90, because that's the average age is going up, your probability of getting Alzheimer's goes up rapidly after 70, and so half the people here could be terminal Alzheimer's someday.
And I guess one last comment, when you're worried about sort of the singularity, once you actually see what we're doing in very specific tasks, I classify, this type of cancer versus, benign, malignant, and so on, you kind of feel like when people worry about the singularity, it's as if kids play Lego and are worried about building a nuclear bomb. It's so unlikely that it's just distracting.
Hi, I'm Vijay again. I had a question about, can the immersive experience open up neural pathways so that you could learn faster?
What a great question. I'll tell you, we struggle with this, okay? We'd like to cure diseases, but as we learn more about the brain, we should be able to develop mental prostheses. And I don't want to say drugs, because very likely it's going to turn out to be a neurotechnology that is quite different from big pharma. In fact, we really think there'll be a neurotechnology industry as important that grows out of the brain initiative as the biotech industries that grew out of recombinant DNA that came from the war on cancer. But the point is, though, that it really will allow us to greatly enhance the way that the brain stores information, processes information. Right now we have ways of, we think, just behavioral ways of improving memory, extreme memory. But it's going to be, with neuroprosthesis and neurotechnology, this could open up a whole new era.
Fantastic. I think we're out of time. Do we have time for one more question, or one more question?
Hi, my name is Nemai. I actually went to Singularity University, so the last question actually really titillated me. But the question that I have is more so about optogenetics and how far are we from mainstream adoption of that into our current day practices.
Okay, so that's my business, and optogenetics, for those of you who don't know about it, is a revolution that occurred about 10 years ago. In fact, up at Stanford, Carl Deiseroth and Ed Boyden. And it's basically using optics. What they did was genetically engineered an algae protein that when you shine a light on it will stimulate a neuron. So by imaging a neuron and simply shining a little beam of laser light, you can activate a whole population of neurons with any pattern that you want. Now, the reason why this is incredibly powerful is that up until recently, the best we could do was just record passively or scoop out the material, lesion it. But now we can actually intervene, and this goes to the issue of improving memory. If we could intervene by putting in patterns that are coming from the outside, we can actually open up a two-way communications between your brain and directly to information sources on the outside, bypassing the senses. Just think about this. Now, it's science fiction today, but I can tell you that DARPA has 2 programs whose goal is going to lead to technologies like this. So this is something that will happen, but when, we don't know.
Fantastic. Well, thank you both. This has been a great panel, and really enjoyed it, and looking forward to the rest of the conference.